Hello, and welcome to today's webinar titled MATLAB Tools for Scientists: An Introduction to Statistical Analysis. My name is Asavi Samant, and I'm an application engineer at the MathWorks. Now, before we get started, a few logistics to take care of. If during today's presentation you have any technical difficulties with either the video or the audio, please communicate that to the webinar host via the chat panel. If you have any questions, please enter those into the Q&A panel, and we'll be answering all the questions in the end. So in today's webinar, we'll be talking about MATLAB as an environment for data analysis and visualization. We'll look at how you can import data into MATLAB, analyze and manipulate that data, do some visualizations, and finally see how to create a report to document or share your analysis. The analysis that will be presented today will have a statistical bent to it. So we'll look at statistical techniques like hypothesis test, analysis of variance, look at different ways of statistical visualizations, look at regression analysis, ways of organizing and filtering your data. All these techniques will be applied to a data set from a fictitious clinical study that investigates the efficacy of a new cholesterol reduction treatment and compares the efficacy of this new treatment to existing drugs. But in general, the techniques that will be presented today can easily be applied to data from a different domain. So before we get started with the actual example, let's look at data analysis from a higher level. So data analysis typically comprises of 3 steps. The first step is accessing your data. So your data might be sitting in some storage format, maybe Excel files, text files, CSV files. It could be coming in from a database or directly be streamed from instruments. So the first step is accessing your data and getting it into your analysis platform. Once your data comes into your analysis platform, you do your number crunching, your visualization, do your analysis with the data, try to ask questions of the data. And then once you have your analysis complete and you have your results, you might want to share those results with others, or you might want to document those results for reference purposes. In some cases, you might want to actually share the analysis with others so that they can repeat the analysis on a different data set. So in today's example, we'll see how you can perform these 3 steps of accessing your data, performing your data analysis, and finally sharing your results, all in a single environment, which will be MATLAB. Also, throughout the process, we'll see how different pieces of the analysis can easily be automated. So that way, when the analysis needs to be repeated or applied to a different data set, you don't have to manually go through these steps. With a click of a button, you can repeat the analysis in a single step. So with that, let's look at today's example. Today we'll be working with a data set from a fictitious clinical study that aims to compare the efficacy of a new drug treatment to reduce cholesterol levels. So to provide with some background, statins are probably the most popular class of cholesterol-reducing drugs in the market. However, studies have shown that statins are not always effective in lowering LDL cholesterol levels to recommended thresholds, even at their highest dosage allowed. So one potential workaround this is combination therapy, where statins are co-administered with another cholesterol-reducing agent, which might have a complementary mechanism of action. So the main hypothesis of this study is that co-administering another drug, we'll call it drug X, with statin is more effective at reducing cholesterol levels than statin monotherapy. The study design consists of 650 patients who had high cholesterol levels, and these patients were assigned to one of the following treatment groups. The first group is the placebo group, which did not receive either drug. The second group is the monotherapy group with drug X, where 10 milligrams of drug X were administered. The third group is the statin monotherapy group, and this has 4 subgroups within it. So the patients within the statin monotherapy group would receive either 10, 20, 40, or 80 milligrams of statin and no drug X. And finally, we have the statin plus X, or the combination therapy group, where 10 milligrams of drug X would be introduced with either 10, 20, 40, or 80 milligrams of statin. Now, for all these patients, lipid profiles, so levels of cholesterol, were measured at baseline, that is beginning before the start of the treatment, and then 12 weeks after a particular treatment was administered. So once again, we want to test the hypothesis that the statin plus X group, that is the combination therapy group in the fourth row here, is more effective at treating high cholesterol than the statin monotherapy group, which is the third row here. The analysis that will be presented in this example today has been modeled after or adapted from this reference at the bottom. However, do note that the data set which will be used is a fabricated data set just for the demonstration purpose. So before we go any further, let me give you a quick preview at where we'll be going today. Here I have a PDF document. Let me maximize this document. That gives you a report of the data analysis that we'll be performing today. So it starts off with the abstract at the top, followed by a description of the data, followed by some preliminary analysis where you visualize the data in a bunch of different ways to identify some trends in the data. And if I scroll down further, we'll be able to see the results of the hypothesis test, the ANOVAs, etc. So the analysis which is shown in this document was done in MATLAB. And you can see the MATLAB code in some of these chapters here. But the more interesting thing about this document is that the document itself was also generated by MATLAB. And by the end of today's webinar, we'll see how both the analysis was done as well as how this particular document was generated. So let me close this particular document. And with that, let us move to MATLAB. So for those of you who have never seen MATLAB or who are new to MATLAB, this is the MATLAB desktop. The big window that you see here with the blinking cursor is the MATLAB command window. This is where you can type in MATLAB instructions and MATLAB will execute those instructions for you. So for example, I can go ahead and create some new variables. I'll go ahead and say A is equal to 1, B is equal to 2, and maybe just go ahead and sum these two. C is equal to A plus B. So as I perform these calculations interactively, you'll see that those variables which I just created have now been displayed in the workspace window. So data created or imported into MATLAB lives in the MATLAB workspace, and the workspace window just displays what is currently available in the MATLAB workspace. However, in most cases of data analysis, you will already have your data sitting somewhere, or you would not be typically creating your data in your analysis platform. In our particular example, our data is sitting in an Excel file called data.xls, and I can see that file is present in my current working directory. So this big window that you're seeing here, the current folder, basically displays the contents, the files and the folders present within MATLAB's current directory. So let's quickly open this data outside MATLAB and look at what the data looks like. So this is the data from the study. Each row corresponds to a different individual or a different patient, and the columns correspond to a different characteristic of the patient or a measured variable. So group B corresponds to the treatment group that the patient belonged to. So group is a categorical variable and it could take one of four values: placebo, drug X, statin, or statin plus X. Columns F and G here correspond to the dosage which was administered. So for the placebo group, you see that the placebo group did not receive either statin, neither did it receive any drug X. But if I scroll down further, the drug X group received 10 milligrams of drug X. Columns H through M correspond to the lipid profiles which were measured. The first three columns correspond to the baseline level as indicated by the underscore BL, and columns K through M correspond to the post-treatment levels which were measured after 12 weeks of treatment. In addition, we also measured some additional characteristics of the patient such as the age, the gender of the patient, etc. So let me go ahead and close this Excel file. So there are a number of ways of importing data from Excel into MATLAB. The simplest way probably is just double-clicking on the Excel file within my current folder here. And what that would do is it would bring up the import wizard, which would allow you to interactively import numeric and text information from this file into MATLAB. However, in this particular case, I will bring this data in as a dataset array using the dataset command. So let me clean my my command window here, and I'm going to use the dataset command. I'm going to specify that my data is coming in from an Excel file, and I'm going to go ahead and specify the name of my Excel file. And finally, I'm going to add a semicolon in the end here to suppress the output from being printed to my command window. So I do not want to see data for 650 patients and 15 columns or so being printed to my command window. So I'll suppress the output from being printed. So I go ahead and hit enter, and you can see now that the data has been imported. And if you look at your workspace window, there is a new variable called ds, which has been imported into my workspace. If I look at the class of ds by clicking on this class option here, you'll see that the class of ds is actually dataset. So dataset arrays are a special type of data container in MATLAB that are ideally suited to work with data tables, where you have rows representing different observations and columns representing different measured variables. The advantage of working with a dataset array is that you can hold heterogeneous information, that is a mixture of text and numeric data, in a single container. So for example, in our data, we have text information stored in the gender and the group column, whereas the other columns, such as the lipid levels, are numeric in nature. And the dataset container will allow us to hold that entire dataset in this single variable called ds. So now that I have my dataset variable created, let me give you a quick introduction to working with dataset arrays. So there are a number of ways of indexing into dataset arrays or working with subsets of information from the dataset arrays. Just like numeric matrices in MATLAB, you can use subscripted indexing. So if I want to pull out information for, let's say, the first row and the fifth column, I can pass in those as the first and the second index within the parentheses, and that gives me the value of the risk variable, the first element in the risk variable, which is the fifth column. If I want to pull out information for a range of row or a range of column values, I can similarly pass in a range. So I can say, give me the first 10 rows and let's say columns 2 through 6. And that gives me the first 10 rows of columns 2 through 6. Notice in this particular case how the name of the group or the name of the column appears at the top. And that brings us to the second advantage of working with dataset arrays, and that is named indexing. What column named indexing allows me to do, it allows me to reference information in any column of the dataset array using this dot suffix notation. So for example, if I wanted to pull out the first 10 values of the age column, I could use the dot age syntax here and say, give me the first 10 values. And that gives me the first 10 values in the age column. If I wanted to extract information for multiple columns, again using the column names, that's possible also. So I'm going to say, give me the first 10 rows in this particular case, and I'll say, give me the first 10 rows for the age, and let's say the ID column. And I'm passing the column names as a cell array of strings here. And that gives me the first 10 values from the age and the ID column. So now that we have our data in, let's start with our analysis. We'll begin with some visualization. Like I noted before, we are going to use the LDL cholesterol levels, that is the so-called bad cholesterol levels, as our primary efficacy endpoint. So let's start by looking at the LDL cholesterol levels before treatment, that is at baseline, and after 12 weeks of treatment. And I'll do this with a simple scatter plot. So I'll use the scatter command in MATLAB, and I'll pass the LDL levels at baseline on my x-axis and the LDL levels after treatment for 12 weeks on the y-axis. Go ahead and hit enter. So we don't see much of a trend here. There are no obvious clusters, just looks like a blob of data. So MATLAB figures, this is a MATLAB figure that you're seeing here. MATLAB figures are interactive, so I could zoom in on a part of the figure, I could pan the figure, rotate the figure, add data tips, etc. In this particular case, what I want to do is I'm going to go ahead and superimpose my means, my x and y means, on this particular figure because I want to see whether the means at baseline differ from the means after treatment. So I'll go to the tools option here. and go to Data Statistics and go ahead and add the mean lines for both X and Y. So if I look at the values here, the mean LDL cholesterol levels at baseline is around 4.2, which is much higher than the mean cholesterol levels after treatment, which is around 2.5. So at least for the pooled data, it seems like the treatment does cause a lowering of the cholesterol levels, the LDL cholesterol levels. Let's close this. If I look at the mean lines here, they're a little faint and you cannot easily see them within the figure. So let's go ahead and modify the appearance a little so that I can make the lines a little thicker. And in this particular case, I'm going to go ahead and customize my plots, make these lines thicker using plot tools. I can open plot tools by clicking on this little icon up at the top. Plot tools essentially is an interactive GUI environment for editing and customizing the appearance of plots in MATLAB. So let's maximize the plot window. And what the plot tools menu allows me to do, it allows me to select different pieces of my figure or my graphic and change its properties. So I can select both the mean lines, come down to the property editor here, make them a little thicker. Let me change the color to red. And while I'm within plot tools, I might choose to do some more editing to my figure. So I might change the markers here. Let's make the marker green. I'll also go ahead and add some X and Y labels and a box around my X's. So this is LDL-C at baseline. Y-axis is LDL-C at 12 weeks. And so I can customize this further, but this plot already is looking much better. So I'll get out of plot tools here by clicking on the little hide plot tools button at the top. So working with plot tools was easy enough to do, but it would be really nice if I can save this customization which was done to the figure so that it can be reapplied or reused at a later time point. So I'm going to go ahead and do that by going to the File menu and selecting the Generate M File option. And what this will do is it will look at your plot, it will see what all customizations were done to the plot and capture the MATLAB code behind these customizations. So in this particular case, it's gone ahead and created a MATLAB function that takes in X and Y inputs and maybe the inputs for the size and the color of your symbol. And inside here is just code that allows you to recreate that figure. Let me go ahead and rename this function. I'll call this LDL plot. And I'll go ahead and save this function. Let's close the editor window. And so now if I wanted to create the same plot, not for the entire data, but maybe if I just wanted to see the placebo group, I could go ahead and reuse this particular figure. So I'm again going to plot the baseline levels on the x-axis, but here I'm going to plot only the first 65 patients which belong to the placebo group. On my y-axis is going to be the post-treatment levels, again only for the first 65 individuals. And I'm going to specify the size of the markers as 50 and maybe make the markers green in color. And so there you go. It goes ahead and recreates the same plot. You can see the customization has been retained, but instead of plotting the entire data, in this particular case, it's only plotted the data or the information for the placebo group. And if you look at the mean levels here, you'll see that the mean levels on the X and the Y axis, that is at baseline and after treatment, are pretty similar at around 4.2 or 4.25. So let's quickly recreate the plot with the whole data. I'll use my up arrow key to access recently called commands, and I'll remove my indices from here so that I'm plotting the entire data instead of just the first 65 rows. So based on the plot with the placebo group, it's obvious that seeing all the groups in a single scatter plot might not be smart, because different treatment groups are probably behaving differently, and those differences are not easily discerned in this plot. So let's go ahead and create a grouped plot instead, where points or rows corresponding to different treatments are color-coded or labeled differently. In this particular case, I'm going to go ahead and use the grouped scatter plot. The function is called gscatter, and it's from the statistics toolbox. And you can see that as I start typing, a little bit of help pop-up appears which gives you the different ways in which this particular function can be used. If I want, I can click on the more help link here, and that will bring up the help file for this particular function. Now all of MATLAB's help is presented in a very consistent manner. So up at the top you'll have the different ways of calling that particular function, followed by detailed descriptions of what the inputs and the outputs mean. And in the end you'll usually have examples of using that particular function, which is very helpful when you want to start using the function. You'll also have in the end a see also section which gives you related functions that you might be interested in. So I'm going to go ahead and use the first syntax here, where I just pass in the x and the y inputs and a grouping input. So let's close this. My x input in this particular case is again going to be my baseline levels. My y input is going to be my levels after treatment. And for the grouping variable, I'm going to go ahead and pass the group column, which corresponds to the 4 treatment groups which were present in my data. Go ahead and hit enter. And there you go. You have this plot which has been created. But now if you look at the plot, the different groups have been color coded, or the different points have been color coded based on the group they belong to. So in this plot, you can clearly see that responses do cluster based on the treatment which was received by the patient. The mean LDL cholesterol levels after treatment are much higher for the placebo group compared to, say, the drug X monotherapy group. You can also see that the LDL cholesterol levels in patients receiving statin, either in statin monotherapy groups or statin in the combination therapy groups, improved much more than patients who received only drug X, so the drug X monotherapy group. We can also see that there's a greater overlap between the statin monotherapy and the combination therapy group. And the other thing you'll notice is the variance along the Y dimension, or the variance of the post-treatment levels, are much higher again in these last 2 groups here. So one thing to remember is that the statin monotherapy and the combination therapy groups did receive 4 different statin doses. And so it could be possible that the variance that we are seeing along the y-axis here is attributed to the different statin dose which was administered. So let's see if that's true by adding the statin dose as a second grouping variable in our group scatter plot. So I'll close this. Once again, I'll use my up arrow key to bring up the last call command. And in this particular case, I'm going to pass in the statin dose as an additional grouping variable. So instead of plotting just using a single grouping variable, I'm using 2 grouping variables here. And what that will do is every unique combination of levels within these grouping variables will be color coded differently. So we do see some stratification here, but the distinction is not definitely as clear as the distinction between, say, the placebo or the drug X group. Primary efficacy metric is the reduction in the LDL cholesterol levels. So let's go ahead and use percentage change in the LDL cholesterol levels from the baseline levels as our primary effectiveness metric. So I'm going to go ahead and calculate this percentage change. And I'm going to add that calculation or that evaluation as a new column to my data set. So I'm going to go ahead and create a new column. I'll call it change underscore LDL. And I'm going to use the difference between the baseline levels and the 12 weeks levels. And then normalize that difference by the baseline levels. I want to multiply it by 100 because I'm calculating the percentage change. Some of you might have noticed that I used a dot before my division operation here. So MATLAB stands for Matrix Laboratory and is designed and optimized to work with vectors and matrices. So by default, the multiplication and the division operators imply matrix multiplication and division. So in this particular case, I wanted to do an element-wise division, which is why I preceded the division sign with a dot. So let's go ahead and create a group plot of our efficacy metric. Again, I'll recall my previously called gscatter command. But in this particular case, I'm going to go ahead and plot the change in the LDL level on my y-axis And on the x-axis, I'm just going to plot serial number or the patient ID. So this is a much cleaner plot than the previous case, and the trends are a little more obvious here. So you can clearly see that the placebo group does not show any improvement. The mean improvement is around 0. The drug X group follows that. It shows maybe around 15% mean improvement, which is not too good. And you see the highest improvement is seen in the combination therapy group. So at least from looking at this plot, it does seem like the combination therapy group, which is the highest block here, did slightly better than the statin monotherapy group. The other thing you might notice is there is a slight linear increase in the effectiveness with respect to doses. So there are two lines that you might see here, which show you a slight increase in the effectiveness as the statin doses increase from 10 milligrams to around 80 milligrams. So based on our preliminary visualization, it helped us identify some trends in our data, draw some preliminary conclusions, and potentially decide our next course of analysis. As an aside, I do want to mention that there are numerous built-in plots to choose from in MATLAB, and just to give you an overview of the kind of things you could do with respect to plotting in MATLAB, let me quickly go ahead and bring up the plot picker. The plot picker gives you a list of all plots which are present in MATLAB, and also gives you access to some of the plots which are available on toolboxes. So everything starting from simple line plots and scatter plots to histograms, pie charts, polar plots. If I scroll on further, lots of nice 3D visualization, and that's just base MATLAB. And in addition, you'll have additional plotting capabilities which is specific to an application area, which will be present under the toolbox plot. So for example, here we have plots which will be commonly used in the controls community. And in addition to all the built-in plots like we saw with plot tools earlier, you can always go ahead and create custom visualization and save them either using plot tools, or you could create them from scratch using functions. So now let's move on to some numerical analysis to quantitatively confirm some of these observations. Our primary hypothesis again is that co-administering drug X with statin is better than statin monotherapy. That is the group that we saw up at the top. Let me bring up this plot again. Our primary hypothesis is that this group at the top here is better than this group. And what we'll be doing is we'll be performing hypothesis test to confirm this hypothesis. So for this, what I want to do is I want to extract the percent change in the LDL levels for only the statin monotherapy and the statin plus X groups. And we're going to be using logical indexing to do this. But before I do that, let me quickly convert the group column from a text variable to a nominal variable. So currently, if I look at the values in my group array, I'm going to take out the unique values only. You'll see that the output here is text information. But there are just 4 categories present within this array. Placebo, drug X, statin, or statin plus X. So in this particular case, it might be more convenient to convert this group column into a nominal arrays. And nominal arrays are better than arrays of string values for 2 reasons. One is that they have a smaller memory footprint, and 2 is we can work with them as if they were numerical entities. So which is oftentimes better than working with text information. So I'm going to go ahead and convert this group variable or group column into a nominal array by using the nominal function. So I'm just going to rewrite the existing data. And some of you might have noticed that the size, the memory of this particular variable went down when I did that conversion. So now that I have converted my grouping variable into a nominal array, I can start extracting the information for the percentage change in the LDL levels for particular groups using logical indexing. So when we introduced dataset arrays initially, we looked at 2 different ways of indexing into dataset arrays. We looked at subscripted indexing and we looked at column named indexing. A third way of extracting or referencing data in dataset arrays is logical indexing, where instead of passing in the row or the column numbers or the column name, I'm going to actually pass in a condition to get a subset of the data where the condition is true. So for example, in this case, we want to extract the mean percentage change in the LDL levels for the statin and the statin plus X groups. So I can go ahead and say, give me the change. I'm going to pass in my condition, and I'm going to say everywhere where ds dot group is equal to statin. And I'm going to store this output in a variable. I'll call it group 1. And so you can see the group 1 variable has 260 elements, so 4 times 65. And similarly, I can go up here and I can say, give me values where the treatment group was statin plus X, and I'll store the values in a variable called group 2. Now if I wanted to look at the mean of these group 1 and group 2, I could use the mean function, and I'll say give me mean of group 1, and similarly give me mean of group 2. And so at least if you look at the mean, seems like the mean of group 1, which is the statin monotherapy group, is lower than the mean of group 2, which is the combination therapy group. But what we really want to test is this difference that we are seeing, is this difference statistically significant? And for that, we'll be doing a hypothesis test. So far I have used a lot of built-in functions from MATLAB, some from the statistics toolbox such as scatter, gscatter, mean, etc. And I knew what functions I should use, and I knew the right syntax to use these functions because I've used them in the past. However, for a new user, it might not always be obvious what the right MATLAB function is or what the right syntax is for doing a particular task. And this is where the MATLAB documentation and help pages can be useful. So for example, in this particular case, I know that I want to perform a 2-sample hypothesis test. So I can go to my function browser, and I can go ahead and say, give me everything you have for a 2-sample hypothesis test. And basically what this does is it goes through your documentation and figures out what functions might be relevant to your search string. So it comes up with a whole list of functions here. Most of them are from the statistics toolbox, if I'm not mistaken. So a lot of different capabilities for performing hypothesis test. Now in this particular case, I'm interested in performing a 2-sample t-test. So I can click on that function. And again, I can go to the function help. We saw the help pages before, and we can go to the function help page to figure out what input arguments should I pass to the function, what's the syntax of calling the function, etc. So I'm going to use just the default syntax here, which is a t-test2, and I'll pass in my 2 groups. So let me go ahead and copy that, paste that into my command window. Let's close these two. And I'm going to replace x and y. In my particular case, I want to test group 1 and group 2. And in this particular case, I can pass in some additional input arguments. I want to say test it at a 99% significance level. And I'm going to perform a left-tailed hypothesis. And what that means is that I'm going to test against the alternative that the mean of group 1 is lower than the mean of group 2. So I'll go ahead and perform this test. And if the null hypothesis is rejected, which it is in this particular case since the output is 1, if it returned a 0, that would mean that the null hypothesis was accepted. So when the null hypothesis is rejected in this particular case, and since we performed a left-tailed hypothesis, we'll accept the alternative hypothesis that group 1 has a lower mean than group 2, which means that the statin is less effective at lowering the LDL cholesterol levels than when statins are combined with drug X. And when you're just starting to work with your data, or if you just want to quickly try a few things, being able to interactively perform the analysis from the command line is very convenient. But as more and more pieces start getting added to your analysis, you might want to save your analysis to work on later, or maybe you want to perform or repeat the same analysis on different data sets. You would like to automate this task or collect all these steps and put them in a single place where they can be run with a single click. So if I want to see what my recently performed steps were, all this while I was using my up arrow key to access my recently called commands, and all those commands are actually stored in the command history. Let me quickly bring up the command history here. So the command history, as the name suggests, is just a history of all the commands which were executed from the command window. so just the log. And I can go ahead and select the relevant commands that I want to include in my final analysis. So I'll just go ahead and select a few here using the control key. We do this. And once I know what commands I want, once I've selected the commands, I can right click and go ahead and create a MATLAB file from my selection. So the script opens in the MATLAB editor window. The MATLAB editor is a full-fledged editor that allows you to edit your functions, your scripts. It color codes the script for better readability, etc. And I can go ahead and save the script which was created by clicking on the save icon here. And I could save this as script, for example. So MATLAB script files are essentially text files with the .m extension, and MATLAB knows how to execute or interpret the text within these files. So I can continue to build my analysis within this script. So I can come in here and edit my script. I can do more stuff with it. But in this particular case, for the interest of time, I'm going to go ahead and open a pre-built script to look at the rest of the analysis. So let me close this particular script file and go ahead and open my pre-built analysis. So the MATLAB desktop is very customizable, so I can move my files, my windows around, I can resize windows, etc. So in this particular case, I've hidden my command history again. And I'm also going to go ahead and hide my current folder and my workspace so that I have more space available, more real estate available to me to work on this or run this particular analysis. So if you look at this script, you'll notice that there's a lot of green text in this script. And you see that the green text appears everywhere where there's a single % sign. So these are comments in MATLAB, non-executable code of your MATLAB, non-executable part of your MATLAB scripts. In general, commenting your analysis is a good practice, and I've added a lot of comments to my script for documentation purposes. Also, you might notice that in this particular script, it has been broken down into smaller sections everywhere where you see the % sign. And these subsections are cells. And cells are helpful because during analysis prototyping phase, they enable you to work only on a part of the analysis without having to rerun any of the preceding steps. So I can run this particular script in a single go by clicking on the run button at the top, which is this little green triangle that you see up in the toolbar. However, for this particular demo, what I'm going to do is I'm going to run this analysis in a cell mode that will enable me to explain each piece of the analysis as it's being executed. So I'll be using these buttons that I'm highlighting right now in the left top corner, and especially the second one, to go ahead and run my analysis in the cell mode. The first few cells in this particular analysis contain analysis that we've already performed from the command line. So I'll skip these cells and we'll pick up after the hypothesis test was done. So this is where the hypothesis test was done, and I'll start from after that step. Let me also clean up my command window. So if you remember, when we did our hypothesis test, we did it on the pooled data. That is, we ignored the level of the statin dose within each treatment group. However, the statin dose might be a significant factor that cannot be ignored. So what we'll do next is we'll add this as another factor and perform a two-way ANOVA, or analysis of variance, to simultaneously understand the effects of both these factors. So we are, in this particular case, we're using the ANOVA N function, again a built-in function from the statistics toolbox. We are performing the analysis of variance on the percentage change in the LDL values, and we are using the statin dose and the treatment group as our two main effects. Now in this particular case, note that we are performing the ANOVA test on a subset of the original data set, and the subset contains only the statin and the statin plus X, which is the combination therapy groups. So go ahead and run this particular analysis, and we can see the ANOVA table has been generated. And if you look at the p-values in this ANOVA results, you'll see that both the p-values are very small, indicating that both these effects, the statin dose as well as the treatment, are significant. So ANOVA indicates that both the effects are significant, but it doesn't give us an insight into the behavior at individual levels. So it doesn't tell us what the specific individual cell means are for the 8 groups, the 4 dose levels for both the treatment groups. So what we'll do next is we'll use the group stats function on the data set to calculate the grouped means. And in this particular case, we're using the statin dose as well as the dose of drug X as the 2 grouping variables. And we are performing our group statistics on the LDL levels, or the percentage change in the LDL levels. So the first 4 rows here in the grouped mean output correspond to the monotherapy, so drug X has 0 dose, and the second 4 rows here correspond to the combination therapy, where 10 milligrams of dose drug X were co-administered with 10, 20, 40 or 80 milligrams of statin. A better way of looking at this data would be by unstacking this data so that we see the effects side by side for the combination and the monotherapy groups. So let's go ahead and use the unstack function, and we'll unstack with respect to the dose value of drug X. So that's a better way of looking at this particular data and comparing the means. So we can see here that at all statin doses, the average efficacy as measured by the percentage lowering of the LDL cholesterol levels was better in the group receiving combination therapy. So if I'm comparing this column here to this column, and in general the second column has higher values compared to the first column here. So both group stats as well as the unstack methods were built-in methods of the dataset arrays. The dataset array has a lot of convenient methods. We showed a couple, there are many more that make it very easy to perform common operations and manipulations on the data. In the next cell here, we're just going ahead and plotting this or visualizing this using a bar plot. The bar command is used here. And so I'm just plotting the means here with respect to the statin dose. And so for both the groups, you can see that with an increase in the statin dose, the percentage lowering in the LDL is increased. So the efficacy of the treatment seems to increase with the statin dose. So let's go ahead and fit a linear regression line to this data, since we are seeing this linear trend with respect to the statin dose. And I'm going to use the entire, instead of using just the means, I'm going to use all the data points to perform this regression. Now, there are a number of ways of doing regression or data fitting in MATLAB. In this particular case, we're going to use an interactive tool called the curve fitting tool, which comes from the curve fitting toolbox for our regression. The first thing we'll do is we'll pull out the information for the X and Y. We're plotting fitting two different data sets here. We are plotting or fitting the percentage change in the LDL levels with respect to the statin dose for the monotherapy group. And then we are similarly fitting the percentage change in the LDL levels or the efficacy versus the statin dose for the combination therapy group. So let's go ahead and extract that data. So we've gone ahead and created our X and Y variables. And next, I'm going to go ahead and launch the curve fitting tool. I want to take a quick aside here to talk a little bit more about toolboxes. I've used the word toolbox quite a few times during this presentation. So basically, we have MATLAB, which is the base platform that provides a rich set of functionality for general mathematical analysis and visualization. But in addition to MATLAB, we have add-on packages called toolboxes that extend MATLAB's functionality into specific domains. So for instance, we have the statistics toolbox, the bioinformatics toolbox, optimization toolbox, etc. And each toolbox gives you a library of built-in functions and interactive tools for performing calculations or visualizations commonly done in that domain. So in this particular case, we are going to use the curve fitting tool from the curve fitting toolbox, which gives you a GUI front end to perform data fitting for two-dimensional data. So I'll go ahead and bring my data into my curve fitting tool. I'm going to go ahead and create two data sets. In the first data set, I'll have X and Y for the monotherapy group. And in the second data set, I'll have X1 and Y1 corresponding to the combination therapy group. So I've gone ahead and brought these two data sets into my curve fitting tool, and you can see that data is plotted here. The top one is the combination therapy, the bottom one is the monotherapy. You can click on the fitting tab here to go ahead and perform my fitting operation. So let me go ahead and create a new fit. A lot of built-in functions to choose from or built-in models to choose from, and if we won't have time to go through all of this, in this particular case I'm going to go ahead and select a simple linear fit because the regression line seems to be a little linear in nature. So I'll go ahead and say apply a linear polynomial to my first data set here, and similarly I'll go ahead and create a new fit and I'll plot a linear regression line to my second data set. So the regression lines get plotted. You can see the results of your fitting analysis. So things like the R-square values, the sum square of errors, the values of the intercept and the slope coefficients calculated, etc. There are many more features in the curve fitting tool that we didn't look at, but if you are more interested in learning about the curve fitting toolbox, you can look at the product page at mathworks.com. So the advantage of using the curve fitting tool, and again a lot of interactive tools in MATLAB also have this functionality, is you can perform a certain operation interactively using a GUI front end, but then once you're done with the operation you can use the generate M file option to capture the MATLAB code behind these interactive action. And the curve fitting tool also has a similar capability. So I can go ahead and generate the MATLAB file here, which would allow me to automate this process or repeat this process on a different data set without having to interactively work in the curve fitting tool. So let's go ahead and close the curve fitting tool. In the next cell here, going back to our script, we are using actually one of these auto-generated functions from the curve fitting tool to go ahead and recreate the plot that we just saw. So in this particular case, I just passed in the two data sets, xy and x1y1, and it went ahead and it recreated this plot which we had seen in the curve fitting tool a minute ago. And it also prints out the output of the fit. Specifically, it gives you the model which was used and the values of the coefficients. So if I bring up this plot here again, in general you'll see that with every doubling of the dose, there's maybe around 5 to 10 point increase in the efficacy that we see. The other thing you might also notice is that for the monotherapy group which received just statin, even at the highest dose, the efficacy that you saw was kind of equivalent to the efficacy which was seen at the lowest dose of statin when administered along with drug X. So what this implies is that if you have certain individuals that cannot tolerate high statin doses, they might be able to get a similar response by administering drug X along with a low dose of statin. Finally, we do some secondary analysis to ensure that the observed efficacy is consistent across demographic subgroups. And we do this using just a visual check, but if you wanted, we could have done a more rigorous hypothesis test or ANOVA in this particular case as well. So we're going to plot it against two different subgroups. I'm creating box plots here, and I'll plot against the age variable as well as the gender variable. And so this shows you box plot, which shows you how males and females compare at different dose levels. And similarly, we have a box plot here, which compares how less than 65 and greater than 65 years, these are two age groups or age classes that I've created, how these two classes compare across the different statin levels. And it seems like more or less they do similarly. But again, this is something that we could check for statistical significance using more rigorous analysis. So this brings us to the end of our analysis. There's a lot more we could have done with our data set, but we have verified our primary hypothesis and also done some secondary analysis and visualization to check for consistency, etc. So one of the advantages of working with a script or having your analysis in script form is now if I wanted to repeat this analysis on a different data set, I could just come up at the top, change the name of my file that I was providing here, and go ahead and click the run button. And so, for example, if I wanted to run the same analysis on a study which combined statin with a different drug, I could have easily repeated my analysis without having to manually go through these steps. So far we've finished the first two steps of our broad data analysis workflow. We've gone ahead and imported our data, we've analyzed and visualized our data, and the last step we want to have is be able to share our work or document our work. I started this presentation with a PDF file that described the analysis that we just did and also had documented the results which were shown here. We are essentially just a click away from recreating that report. So if I click on this little flying page or speeding page icon up at the top, what's going to happen is MATLAB is going to go ahead and execute this script. So it's going to run through all the cells within this script. But at the end, it's also going to go ahead and create a report. My default report option in this particular case is going to be an HTML document. And so it's executing the script right now, generating all the plots. And there you go, you have your HTML report. So notice how in this report each of the cells have now become subsections or chapters within this report. All the comments that I added to my analysis are now textual description. And if I scroll down further, you'll be able to also see the MATLAB code which was actually executed along with any plots which were generated. So this was another custom plot which I had added to my script. And also any results of your analysis. So if I scroll down further, you should be able to see things like results of the hypothesis test. So the publish feature is a nice one-click feature which allows you to easily convert your analysis into document. In this particular case, we created an HTML report, but the other output options are Word documents, PDFs, which we saw earlier today, LaTeX documents, PowerPoint presentation, etc. So that brings us to the end of our demonstration. Let me quickly go back to my slides. So we looked at an example of performing a data analysis example in MATLAB. We went through the basic steps of importing our data. We did a lot of statistical analysis and visualization as our second step here. And finally, we shared our results and our analysis via a report. In this particular example, I used MATLAB, the statistics toolbox, and the curve fitting toolbox for my analysis. But what I would like to do next is quickly go through some of the other things which are also possible. With respect to import, we imported our data from an Excel file, but you could also have imported from text files, binary files. You could have brought in data from databases, SAS transport file, directly connected to hardware. And this is just stuff within base MATLAB. In addition, toolboxes would support additional proprietary formats which are specific to that particular domain. MATLAB plays well with a lot of different input formats. With respect to analysis, we barely touched the tip of the iceberg with respect to what's available in MATLAB. It has a whole slew of built-in features for math and engineering calculations, a whole array of built-in plots. We looked at some of them. But in addition to what's available in MATLAB, each toolbox also adds a lot of good functionality. We looked at some of the basic functionality in the statistics and the curve fitting toolbox, but there are also additional tools for bioinformatics, optimization, neural networks, PKPD modeling, mechanistic modeling functionality exists in SimBiology. There are tools for parallelizing your work. And so if you need more information on any of these tools, again, you can visit our website at mathworks.com. Second excellent resource for getting more information on specific tools are our recorded webinars. So if you go to the MathWorks webpage, you'll be able to go and look at the webinars for a particular product. So for example, here are just a few webinars which might be relevant. So that brings us to the end of our presentation. I thank you all for your attention, and I hope this talk was helpful. We'll go offline for a moment now to look at all the questions that came in during the presentation. If you have any questions right now, please type them into the Q&A panel. We'll be back in a minute to answer all the questions. Thank you.